This was one of the more surprising results to me as I was learning about electromagnetism, but the electric field itself has an associated energy density of 1/2 epsilon naught times the magnitude of the electric field squared at that point. So how do we derive this? Well, the place to start is with a capacitor, because of its simple field. But at the end, I'll explain why the equation we have generated generalizes to all electric fields. The definition of capacitance is the ratio of charge on the capacitor to the potential difference between the plates. This can be simply rearranged to give that the potential difference between the plates is the charge on the plates divided by the capacitance. Next, the question is, what is the energy stored in this capacitor? We know that it can be used to drive current in a circuit, so there must be some kind of energy there. We figure this out by considering the tiny amount of work needed to move a small charge across a potential difference. So the total work would be the integral of the potential difference with respect to charge. And the potential difference is Q over C, as we saw. So let's sub that in. The bounds of the integral are from 0 charge to Q charge, because we are going from 0 charge on the capacitor to Q charge. This is one of the easier integrals you'll encounter in physics. Just do the reverse power rule and you should be good. So the work is Q squared over 2C. Meaning the energy of the capacitor is equal to 1/2 CV squared. I was able to make that leap by multiplying the numerator and denominator by C, and seeing that we have a Q over C that we can turn into a V. Alright, so now we're ready to bring the electric field into the equation. Remember that the potential difference is just the integral of the electric field dotted with displacement, and that because the electric field is constant in a capacitor, we end up with the simple equation V equals E times D. D being the distance between the plates. If you're unsure about this result, watch my video deriving the capacitance of a parallel plate capacitor. In fact, here's a spoiler, you're going to need to know that formula as well. Alright, so let's sub that expression for V back into our equation. Now, in a sense, we're basically done. But this is an equation for the energy, not the energy density, and it still includes the capacitance, even though we want this to be a general formula. No need to worry though, we know that the capacitance is epsilon naught times A over D, where A is the area of the plate. So we can sub that in and notice that a D cancels out. Now the energy density is the energy divided by the volume enclosed, and the volume of a capacitor is just A times D, right? The area of the plate times the distance between the plates. And I'm sure you're already getting ahead of me here. You can see that the AD cancels out on the numerator and denominator, so we have an equation for the energy density of the electric field. Now, why does this generalize to any electric field? The way that helped me think about it is, consider we started with a very tiny capacitor at the beginning. We would still have ended up with the same formula, right? But if you're looking at general electric fields, and then zoom in really close into that general electric field, in that tiny region, the electric field is basically constant. So a tiny region of any electric field kind of just looks like a capacitor. So the energy density as a function of position is just the tiny energy in the field divided by the tiny volume. But we know that the tiny energy is just the equation we came up with, except of instead of an AD, we have a dx dy dz in our numerator, and our denominator, in fact, for the volume. Either way, they cancel out on the numerator and the denominator, so our general formula for the energy density of the electric field is 1/2 epsilon naught times the magnitude of the electric field at a specific point squared. I hope this was helpful and that the derivation was enlightening. If you have any questions, please leave them in the comments, and be sure to check out some of my other videos, such as a derivation of the capacitor discharge equations, and a derivation of the formula for the capacitance of a parallel plate capacitor that we used in this video. Thanks for watching, and bye-bye.